Today our lesson is titled More on Matrices. So in our last lesson we learned how to solve systems of equations in three variables using matrices. But just as in systems of equations in two variables, you may encounter systems with no solution or infinitely many solutions. So let's review some of those special cases. So for two variables, graphs of linear equations in two variables appear as straight lines on a graph, okay? So when you graph two linear equations on the same graph, you can get three types of solutions. The first type is if the lines intersect, you'll get one unique solution. And your solution is going to be some ordered pair x, y. Another case is if the lines are parallel and they never cross. Well, in this case, you don't have any solutions, so you can just write no solution. And the third case is if the two lines are lying on top of each other. I'm not sure if you can tell, but we have a red line on top of a blue line right here. And so because they're lying on the same line, there's infinitely many solutions. Now, just saying that there's lots of solutions isn't a good enough answer because just because you have a lot of solutions doesn't mean every solution works. Let me show you here. All of the points on this line are solutions to the red line as well as solutions to the blue line, every single one of them. But if I just pick any random point like this point out here, that is not a solution. So yes, there's a lot of solutions, there's infinitely many solutions, but it's not all solutions. For example, this one out here doesn't work, but there's an infinite amount on the line that does work. So when I'm saying that there's infinite amount of solutions, you have to go a little bit further and just tell me what the solutions are. In two variables, we use set notation. We say the set of all x, y, such that line there is such that, and then the equation of the line. So y equals whatever the equation of the line is. So this means the set of all points that lie on the line. So there's lots and lots of solutions, but only the ones that lie on the line. So let's look at the situation for three variables. So graphs of linear equations in three variables don't appear as straight lines like they did in two. They appear as two-dimensional planes. So when graphing three equations on the same graph, you can get three types of solutions. The planes can intersect at a single point. So the light blue, the medium blue, and the dark blue all intersect right there at that intersection point. So you get one unique solution. And your solution is going to look like an ordered triple, like x, comma y, comma z, or an ordered triple. Those are the ones that we've already covered in the previous lesson. The next two are the two that we're going to be working on today. So the second choice is if planes are parallel or that they cross, but they don't all three cross at any common points. So the two choices are they can either be parallel, like the first case where the first plane, the second plane, and the third plane are all parallel and have nothing in common, or that two of the planes intersect but the third one doesn't intersect at the same spot. So down here we have the three planes do intersect at three different places, but all three planes don't intersect at any place at all. So in this case, there is no solution for all three equations in three variables. And then the last case is if the planes coincide and intersect at a line or a plane or at lots of points, okay? So there's one example that I showed you. The three planes here intersect at this line right here in the middle. So that line in the middle satisfies both the light blue, the medium blue, and the dark blue line. So how many solutions do you have? You have infinitely many solutions. But just like in two variables, telling me that there's lots of solutions isn't actually sufficient to tell me what the solutions are. Yes, there's lots of solutions. Anything that's on this line, all these points are solutions, But a point way out here, that's not a solution. So it's not every solution in the world, but there is a lot of them. The way we write that is we're going to be writing an ordered triple, but in terms of one variable. We'll say a new variable, which we'll show you in a few minutes. An example would be like 2t minus 3, t plus 7, and t, where if I plugged in any t, I would get an ordered triple that does lie on the line. This is more of a vector form of answering it rather than the set notation that we did in the two variables. Next, I want to interpret row echelon matrices in their special case situations. So the first one, we have the matrix. I've already done all the row operations, so it's already in row echelon form. So I'm going to change it back into the equation form. Okay, so how many solutions are you going to get on this particular problem? Well, you're going to get one unique solution, meaning there's only one that works, and these are similar to what we've done in the past. So if I use the space down here to try to solve it, I'm going to move these two to the other side to get negative 5y plus z minus 1. On the next equation, I'm going to move the z over, so I get y is equal to negative 4z. Moves across the equal sign, so it changes sign. And then the last one, z equals 3. So I have a solution for z. To get the solution for y, I'm going to back substitute. I'll plug in 3 for z. When I evaluate, that's going to get me negative 12 plus 13, or 1. And then I'm going to use the x equation, plug in the y and the z to solve for x. So that gets me negative 5 times 1, which is negative 5, plus 3, which is negative 2, minus 1 is negative 3. So my one unique solution using back substitution is negative 3, 1, 3. So if I can get my equations to have ones down the diagonal and zeros below, then I can get one unique solution like we've done in the past lesson. Our next problem has ones down the diagonal almost. We have a problem here. We have a 1 and we have a 1, but we were trying to get a 1, but we accidentally zeroed out that part of the equation. So, and this is one of those special cases. I was trying to get ones down the diagonal and zeros below, but we had a little hiccup here. I was planning on doing it, but it kind of just didn't work out. That's not my fault. That's how the equations worked out. So when I rewrite this into the system of equations, my last equation says 0 equals 4. That is a problem. If we ever have 0 equals a number other than 0, well, that's just not true. And because this is not true ever, 0 is never going to equal 4, I can automatically stop and write there is no solution to this problem, and my solution is just the null set or empty set. Okay, let's look at the next one. Again, I'm trying to find ones down the diagonal. 1, 1, uh-oh, we have another problem here. Let's say we were doing our row operations, we were trying to get ones down the diagonal with zeros below. I was doing okay until the last step, and then the 0, I had a 0 there instead of 1, and there's no way to get a 1 there if it's already a 0. So we have a problem again. So let's write out the equations. We have x minus 2y plus 1z equals 4. We have y minus 3z equals 7. And then we have 0 equals 0. Well, that last equation is technically a true statement. Not only is it a true statement, but it gives us lots of variation for what we could choose for z. So in this case, we are going to have infinitely many solutions. But that's just not sufficient just to say, oh yeah, there's a lot of solutions, because it's not all real solutions. It's just there's a lot of them. So we need to describe them a little bit more thoroughly. So what I'm going to do is I'm going to solve for my equations for x and y. So I have x equals positive 2y because I moved it to the other side, minus z because I moved it to the other side, plus 4 because the 4 stayed on the same side. For my y, I have y equals the 3z moves to the other side. The 7 stays positive. And then the last situation, I don't have any more equations. So what we're going to do is we are going to let z equal some variable. Now most of the books that I've seen use the letter t, but technically you could use whatever letter you want. And what we're going to do is we're going to find the equation in an ordered triple in terms of t. So if I say z is going to be t, so I'm going to go ahead and just label z as a variable. Then I can back substitute. I have y equals 3 times z plus 7, but instead of z, I'm going to plug in t. Well, that's just simply 3t plus 7. So my y variable in terms of t is 3t plus 7. And then to solve for x, I have 2 times y minus z plus 4, where my y is 3t plus 7, and my z is just t. So if I reduce or simplify here, that gets me x is equal to 6t plus 14 minus t plus 4. So when I combine the t's, I get 5t. When I combine the numbers, I get plus 18. So x is equal to 5t plus 18. So the infinitely many solutions written in vector form is 5t plus 18, comma, 3t plus 7, comma, t. This is the ordered triple, and it tells us lots and lots of answers. So to make that just a little bit more clear, I want to show you how that actually tells us an infinite amount of solutions. Let's let t equal some number. I don't really care. Just pick any number that you like. I guess we'll go with 1 here. If I let t equal 1 and I plug that in to my ordered triple, I have 5 times 1 plus 18, 3 times 1 plus 7, comma, 1. 5 times 1 is 5 plus 18 is going to be 23. 3 times 1 is 3 plus 7 is 10. So this is one of the infinitely many solutions that truly does work. Let's just make sure. If you take this solution, one solution, and plug it in to your equations, we have x, which is 23, minus 2 times y. Let me go ahead and write this out. 23 minus 2 times 10 plus 1 is supposedly equal to 4. So 23 minus 20 is 3 plus 1, truly is 4. It works. And if you plug it into the other one, it's going to work as well. Y, which is 10, minus 3 times 1 is truly 7. Okay, so this one solution of the infinite many does work. If you want to pick another solution, just pick another number. So the first time we did t is 1. Let's try t is negative 2. You can try all sorts of things. So I have 5 times negative 2 plus 18 for x. Then I have 3 times negative 2 plus 7, and then negative 2. So that gets me negative 10 plus 18, which is 8. Negative 6 plus 7, which is 1, and then negative 2. So this is another one of the infinitely many solutions. If I plug it in, it will also work. So if I do 8 minus 2 times 1 plus a negative 2. That's 8 minus 2 is 4. Yep, it works. How about 1 minus 3 times negative 2? Yes, is 7. So this one works as well. So those are two of the infinite amount of solutions described by my vector form of the solution for the infinitely many solutions. Now, that means there's an infinite amount of solutions, but if you just pick some random number, so if I just pick some random 1, 2, 3, and I plug it in, it's not going to work. It's not any old number, okay? It's the ordered triples that have the relationship of 5t plus 18, 3t plus 7, t. So that's how we describe infinitely many solutions.